We'll continue with parsing, probably one of the most successful branches of linguistics and natural language processing, both language insight-wise and computational results-wise. Now, as usual, we do a recap of the week that went by. So the 5th week of 19th August, we started parsing, and a very, very important insight was that the notion of parsing or notion of an internal structure was inevitable from the observation of the following language phenomenon. The language phenomenon is that if we have a sequence of language constructs, language entities, maybe characters, phrases, sentence, words, even though the sequence is same, it has more than one meaning. Just like in case of arithmetic expressions involving multiple operators, if we do not use any rule of precedence, then there is ambiguity, and multiple values can result from the computation of the numbers and operators. So the example that is shown here is a sequence of 3 integers, 3, 4, and 5, and 2 operators, plus and star. So the sequence is 3, then operator plus, then 4, then operator star, and then operator 5. Now this sequence can have 2 values. It can be 3 plus 4 into 5, which is 23. Or it can be 3 plus 4, 7 into 5, which is 35. There are 2 values. And we know that the correct value is 23 because star is given higher precedence over plus. So we have to compute 4 plus 5 first, and then produce the result, which is 20, and then add 3 to it, 23. So the point to note here is that there is a sequence of 3 integers and 2 operators in between them. The same sequence gives 2 values. Why is it so? Coming to the language side, consider the word unlockable, which has these characters UNLOCKABLE and 3 morphemes un, lock, and able. So this particular string of characters or string of morphemes again has 2 different meanings. One possibility is take out the prefix un and process lockable as a meaning unit. Lockable is something that can be locked. Unlockable is something that cannot be locked. So for example, this door cannot be locked because its hinge has jammed. So the door is unlockable because its hinge is jammed. The other meaning is unlock and able. Now you associate un and lock with higher precedence, and then suffix unlock with able. The meaning here is something that can be unlocked, that can be unlocked. So I have the key to the lock, and this door is unlockable by me. I can unlock the door because I have the key. So again, 3 morphemes, a sequence of 3 morphemes has 2 different meanings. How is this possible? This is possible only if we propose that unlockable has 2 different structures. Un as a prefix, and then lockable, which is breakable into lock and able, or it is unlock, which is breakable into un and lock, and then able. So the existence of a deeper structure comes from the fact that the sequence of entities gives rise to 2 different values. Values in case of language means meaning. So this phenomenon is called structural ambiguity, one of the most interesting and powerful challenges in language processing. Then we discussed two kinds of parsing, constituency parsing and dependency parsing, about which we'll make further remarks as we move forward. And we understood the importance of part of speech tagging in the whole structure called NLP stack. Part of speech supplies information to the next higher level, which is the level of shallow parsing or chunking. And moving up further to deep parsing, which produces a deep tree. So here, for example, we have the parse tree of a noun phrase, which consists of determiner, DT, and a noun phrase. So DT and NP together form this noun phrase. NP in turn consists of an adjective phrase, which can be one or more adjectives, and an NP, which can be a single noun, fox. So the brown fox, though a linear sequence, has a deeper structure in the form of the tree shown here. So this is facilitated by part of speech because the has to be correctly given the grammatical role, which is determiner, brown adjective JJ, fox noun NN. Now, parsing is important in many downstream applications. One of the examples is sentiment analysis, and especially aspect-based sentiment analysis. In aspect-based sentiment analysis, an opinion holder holds a sentiment, positive, negative, or neutral, about a particular aspect of an entity. For example, the songs of the movie was good. However, the choreography lacked imagination. So choreography has attracted negative sentiment. Songs have attracted positive sentiment. And this aspect and the sentiment, that association is made quite simple if we have run dependency parser on the sentence and extract the associations. In modern days, natural language processing based on transformers, LLM, etc., this kind of aspect sentiment association is well achieved by what is called attention, self-attention of pairs of words or pairs of phrases within a sentence. The next very important development in linguistics, of which NLP was a beneficiary, was the arrival or advent of context-free grammar, more generally generative grammar. So a set of context-free grammar rules have the power of generating language constructs, strings of language elements. So here, for example, we see two context-free grammar rules. S goes to NPVP. That means a sentence is composed of noun phrase and verb phrase. Noun phrase is composed of noun phrases again and preposition phrases. The second rule is recursive. NP calls itself again, and it can do so infinite number of times. So a generative grammar, though has finite number of elements in it, can give rise to infinite number of constructs. So this was a milestone in linguistics because it showed how to capture an infinite set by means of finite representation. This was indeed a very important progress in linguistics and computational linguistics. This is very computational in nature. Recursion, which is used in programming languages for various purposes, came actually from linguistics from the notion of generative grammars. Then we looked at some important algorithms for parsing, top-down and bottom-up and CYK. We would like to take a look at the combination of top-down and bottom-up parsing today. And an important element of language processing was introduced in the form of BI notation. This is very sacrosanct in NLP. B indicates beginning of some language construct. EI indicates elements which are inside, I means inside, that language construct. This is what we did last week. I'll just repeat two important points. The notion of structural ambiguity and the position that linear sequences have deeper structures. And the second very important, powerful concept of generative grammar, whereby finite number of rules, we can generate infinite number of language constructs. Moving forward, we would like to deepen our understanding of parsing and syntax. We would like to make some observations on shallow and deep parsing. Let us look at this tree in front of us. In computer science, we have inverted trees, right? The root is at the top and the branches of the tree develop downwards, unlike an actual real tree. So this S is the starting element. S stands for a sentence. And the two children, NP and VP, say that NP and VP are constituents of S. This is the meaning of parent-child relationship, and we'll very soon see what is the meaning of sibling relationship in constituency parsing. Parent-child relationship in constituency parsing describes the constituents by which a phrase can be formed. A sentence is also a large phrase in the limiting case. So NP and VP are the constituents of S. Now under NP, we see a triangle. What does this mean? So let us get used to the terminology, definitions, and expressions in syntax or parsing. So Air India Women Pilots has its own internal structure, but we are not showing it here. We are capturing or abstracting that internal structure out by drawing a triangle here, indicating thereby that I'm not showing you the details, but Air India Women Pilots is not an unbreakable, not an unprocessable integral language construct. It has an internal structure. On the other hand, VP is being detailed out. VP has V as a constituent and NP as a constituent. And which is the V here, fly? This is the main verb. NP here consists of a single preposition phrase. Preposition P and NP. P is over and NP is this two-word sequence, not four. The triangle indicates that I'm not showing you the details, but it has its own tree. So this is the parse tree, and we have several important things to know about it. We first understood the meaning of parent-child relationships. The children form as constituents the parent. Next, let us try to understand the meaning of the sibling relationship and also the notion of head and modifier. If we have a VP, that means a verb phrase, there has to be a verb in it. A verb phrase doesn't make sense unless it has a verb. We will not be able to call it a verb phrase. And that verb is what is called the head of the phrase. So in a phrase, we have multiple words, and one of them has a special status. It is called the head of the phrase. And always the head of the phrase matches the type of the phrase. So if the phrase is a verb phrase, the head has to be a verb. If the phrase is noun phrase, it has to be a noun, N. And NP consists of PP. PP again has the head as a preposition, which is over, and NP, which is its sibling. Now, what is the role of the non-head sibling? The non-head sibling is called a modifier. So in a preposition phrase, over is the head, North Pole here is the modifier. In what sense is North Pole a modifier? How is it modifying a preposition phrase? Well, the notion of modifier is very general, and the notion of modifier means that it has some semantic role to play with respect to the head. So in this case, North Pole is called the prepositional object of over. So North Pole serves as the object of over. We know that a preposition cannot by itself stand in a sentence. So it needs a noun phrase to complete its desire. In Sanskrit linguistics, it is called akanksha. Preposition has an akanksha of a noun phrase, which the North Pole meets. So North Pole is modified in the sense of being an object for the preposition. In what sense is the NP, which is the sibling of V of fly, a modifier? Well, if a verb is transitive, it has the akanksha or desire of a noun phrase. So fly over North Pole is serving as the object of this transitive verb fly. In that sense, it is the modifier. The notion of modifier is most apparent in case of adjectives and nouns. Adjectives modify nouns, and it is made apparent from the parse tree. So I've written a small note here. The sequences Air India Women Pilot and North Pole will not be further expanded in shallow parsing. Shallow parsing is called shallow because of this. It doesn't expand further a phrase. Deep parsing will not stop until all the tokens or terminals are uncovered. That is, the actual words are reached. Here is an example of B and I labels in operation. Air India Women Pilots. We have a B at Air. India I, Women I, Pilots I. So these B and I are inside a chunk. What kind of noun chunk? Noun chunk. So Air India Women Pilots is a noun chunk which is doing the act of flying. So here target phrases are Air India Women Pilots and North Pole. Again in North Pole we have B and I. Pole is inside that chunk, North Pole. Now chunk extraction you can easily see is a sequence leveling exercise. If we have to extract noun chunks, then we'll have to identify those noun and adjective maybe sometimes and other noun sequences and label them as with B and I labels. So here Air India Women Pilots will be labeled by B, I, and I. This can be done by making use of local information. We look at a word and decide whether it should get a B or I. That depends on the word itself and the information around it that is in the context. So B and I labeling is also a sequence leveling problem. It can be solved using the our usual argmax computation. We have to produce labels at various positions. And of course, we'll have to use the features on that position and around that position if you're using a discriminative modeling approach. Generative modeling is also possible, but in case of shallow parsing, it has been found that features need to be used. And that points to use of discriminative modeling. Now, let us take a very famous sentence from linguistics. I saw a boy with a telescope. It is used umpteen number of times in linguistic discussions, especially for discussing syntax and structural ambiguity. I saw a boy with a telescope has two meanings. I have the telescope and I'm seeing a boy, or I am seeing a boy who has a telescope. I was seeing a boy who has a telescope. So the same sequence has two meanings. That means it must have a two deeper structures. So it must have two parse trees. This indeed is the case. S goes to NP and VP. NP and VP are the constituents of the sentence. NP goes to N goes to I. So here with a bit of liberty with notation, we have looked up an I also has it as a noun. Actually, it is a pronoun. So NP it consists of only the word I, which is a pronoun. And VP consists of a deeper structure V, which is saw, main verb. And then we have an NP, which is complex. This NP has three children, DET, determiner A, N, noun, boy, and a preposition phrase with a telescope. Now, let us apply the rule of parent-child relationship and sibling relationship. NP having children DET and PP means that a noun phrase consists of a determiner, noun, and preposition phrase in that order. So order is important in English. So in that order must be maintained. And since it is a noun phrase, its head can be only a noun. So boy is the noun. Therefore, DET and PP must be modifiers. DET coming before boy is called a pre-modifier. Okay, it modifies boy. Which boy? A boy, some boy. PP is also a modifier. It is called a post modifier. It is coming after the head. And what does it modify? The boy. Which boy? A boy who has a telescope. Under PP, we again see with and a telescope. A telescope is the modifier of with. So this kind of parent-child and sibling relationship is very, very fundamental. And we should be absolutely clear about these relationships and how they contribute to the formation of parse trees and phrases. So the hallmark of constituency parsing is the constituent phrases which come together to form a sentence, and sub-phrases come together to form phrases and so on recursively. So in this case, we say that the boy has the telescope. What is the reason for that? We look upon PP as the modifier, and we see that from boy, the path distance to PP is 1, 2, 3 arcs. And from saw, it is 1, 2, 3, 4 arcs. So we apply a principle called sannidhi or proximity, nearness. And we say that since the prepositional modifier with a telescope is closer to boy, it must be modifying boy. So is there also a diagram to show that I have the telescope? Yes, indeed. This is the second parse tree. Here we see that the verb phrase has three children, V, NP, and PP. So the verb phrase consists of three constituents, the verb, a noun phrase, and a preposition phrase. Noun phrase is a boy, preposition phrase is with a telescope. So who is the head and who are the modifiers here? There are three siblings, three children, so there must be one head and two modifiers. Since this is a verb phrase, saw a boy with a telescope, its head must be a V. So V, saw is the head. In what sense is a boy modifier for saw? Yeah, well, it is the object of saw, which is fine. With a telescope, it could have been a modifier for boy or saw, but since it is a sibling of the main verb saw, it must be modifying saw and not boy. That is the syntactic argument. So PP is modifying saw, which means with a telescope is attached to saw. Attached with what relationship? With the relationship of instrument. The telescope is coming as the instrument of seeing activity. So if seeing is the having the modifier as with a telescope, and with a telescope actually means the instrument, then who has the telescope? So seeing is done by whom? Boy is not doing seeing. I am doing the seeing. So I have the telescope. This is how from syntax we go to semantics. Does the Sannidhi principle apply here? It does. So PP is the modifier. So from saw, I have 1, 2, 3 arcs. The path length is 3. What about from boy? From boy, it is 4. 1, 2, 3, 4. Y to N, N to NP, NP to VP, VP to PP. So 4 arcs. So again, Sannidhi principle is helping. So these are the two parse trees, and we are able to see how two different syntactic structures are indicating the presence of two different meanings for the same sequence of words. In other words, the sentence has structural ambiguity. The foundation of constituency tree we have already discussed. The parent-child relation means the parent is constituted of children. If there are multiple children, there is multiple constituents. One of them has to be the head, others are modifiers. Thus, given VP going to V and P, VP is constituted of V and NP. P is the head and NP is the modifier. Let us take the other approach to parsing. This is called dependency parsing. And in dependency parsing, we have the advantage of dealing with free word order languages. If you recall, we said that in one of the parse trees where I saw a boy with a telescope, the VP had 3 constituents: determiner, noun phrase, and preposition phrase. You cannot take liberty with the order of these phrases. First determiner, then the noun phrase, then the preposition phrase. You cannot put preposition phrase before. But that restriction does not apply in case of languages which allow free word order. I saw a boy with a telescope. I saw a boy with a telescope. I saw with a telescope a boy is idiomatically not very acceptable in English. Such constructs appear in non-canonical forms. What is called non-canonical form? Maybe in poetry. I saw with a telescope a boy. Okay. But in Hindi, this will not sound unnatural. In fact, with a telescope will not go after the noun at all. Hindi doesn't have preposition. Hindi has postposition. So I saw with a telescope a boy. मैंने एक दूरबीन से एक लड़के को देखा. एक दूरबीन से मैं एक लड़के को देखा. So दूरबीन से, this can be moved around. This is the property of free word order languages. So there the constituency parsing will run into a lot of difficulty. Not so if you adopt dependency parsing. In dependency parsing, we directly encode the dependency between head and modifier. That dependency is indirectly expressed by means of sibling relationship in a constituency parsing. In dependency parsing, this dependency information is directly encoded. So I and saw has agent relationship. First of all, we have to identify the main verb in dependency parsing. Saw and I is the agent. What did I see? A boy. That's my object relationship. Which boy? A boy. That's my modifier. Another modifier with a telescope. With a telescope is a modifier for boy. So this head and dependency is immediately seen in the dependency parse tree. Now, since the sentence has two meanings, is it the case that it has two dependency trees also? Indeed, it is true. So here we see the case where I have the telescope. I am the agent of saw with a telescope is the modifier for saw. That means it has some semantic relation directly with saw. So this means that I hold the telescope, and this relationship is instrument relationship. So this is the characteristic of dependency tree. Therefore, we can again discuss the foundation of dependency tree just like we did for foundation of constituency tree. Parent-child relation is head modifier. Parent-child relationship is not constituency, as in constituency parser. Parent-child relationship is head modifier. The head modifier relation is further specified. So label DT means labeled dependency tree. You can have dependency tree which is unlabeled. That's called unlabeled dependency tree. In case of labeled dependency tree, the arcs are given labels. So for example, if I is a subject of I saw the boy with the telescope, then I being the subject, the arc will be labeled n subject. But we have shown agent. That means we have given a more specific semantic relation. N sub means nominal subject. Then D obj is direct object, I obj is indirect object. So here is a sentence with three noun phrases: Jack, a book, and Jill. And the main verb gave has relationships with these noun phrases. Jack is n sub, it is the subject. A book, book is the direct object. To Jill, Jill is the beneficiary. This is called I obj, that is indirect object. So we have seen how to interpret the arcs, parents, children, siblings in constituency tree and dependency tree. Now we were using syntactic tree to arrive at correct meaning. From the structure, the meaning became apparent. Now we are saying meaning many times. Is there a strong connection between meaning and structure, between syntax and semantics? It turns out that this is not the case. You can have completely meaningless sentences with perfect syntactic tree and syntactically wrong sentences with still able to convey meaning correctly. So this sentence is very famous due to one of the most celebrated linguists our field has seen, Noam Chomsky from MIT. Colorless green ideas sleep furiously. It's a very well-known sentence. And the sentence doesn't have meaning because of several contradictions. First of all, how can something be both colorless and green? This is a contradiction. How can ideas have color? Green ideas doesn't make sense. How can anybody sleep furiously? Sleeping is a peaceful activity. Sleep and furiously do not go together. So that's a wrong construct. So colorless green ideas sleep furiously has no meaning. It has no meaning or zero meaning, but it has a perfectly constructed syntactic tree. S goes to NP, VP, NP goes to adjective phrase, and NNS, now plural noun. Adjective phrase is a collection of more than one adjective, so colorless and green. And VP, verb phrase, has a structure of verb and adverb, sleep furiously. So nothing prevented me from drawing the syntactic tree of the sentence. So this shows that independent of semantics, given the grammatical rules, we can form the syntactic tree of any nonsensical sentence also. Now, this supports the brain phenomenon. The brain, we know, has two designated areas which are physically separate from each other. Broca's area in the brain deals with syntactic correctness. It understands syntax and forms sentences which are syntactically correct. While uh, Wernicke's area in the brain handles semantics. That semantics corresponds to meaning. And if there is any damage in the Wernicke's area, the patient produces perfectly syntactic constructs without any meaning at all. And Broca's area damage messes up the syntax, though the semantics may be absolutely fine. Tea drink, which means I'm drinking tea and I'm conveying that idea fine, absolutely fine, though the syntax has been messed up. So this notion that syntax and semantics can be separate is also a very important language concept. Computationally very convenient. We can concentrate on different layers of the NLP stack without bothering about what happens in other layers. We can be locally focused, concentrating on syntactic algorithms without worrying about what is happening to semantics. Though eventually we'll have to, if there is a downstream NLP application involving syntax, semantics, everything. For example, this would happen in question answering. A chatbot has to be syntactically and semantically correct to carry on a meaningful conversation with an interactor. We can also construct the dependency parse tree of these nonsensical sentence, colorless green ideas sleep furiously. All we have to do is to first identify the main verb. Main verb is sleep. And then we see that furiously is an adverbial modifier to sleep, which is fine. Ideas is the subject, therefore nominal subject ends up. And we have two adjective modifiers, a mod, colorless and green for ideas. Even though they do not mean anything, we are able to draw the dependency relationship between ideas, colorless and green. So syntax and semantics influence it, but they can be independent too, as in the case of colorless green ideas sleep furiously. And this is consistent with neurolinguistics, Broca's and Wernicke's area, which keep syntax and semantic processing separate. Now, we discussed grammar and parsing algorithms last time with a very simple grammar. S goes to NP-VP, NP goes to DTN or N, and VP goes to VADV or V. That means the noun phrase can be consisting of an article and noun combination or a single noun. And the verb phrase also can also be constructed in two ways, verb adverb combination or just verb. So the above captures a declarative sentence. And there are, we know, four kinds of sentences as per traditional grammar. Declarative, sun rises in the east. Interrogative, does sun rise in the east? Imperative, rise in the east, please. And exclamatory, oh, sun rises in the east. So these are four types of sentences as per traditional grammar. Now we use this simple grammar to parse a sentence. Okay. The sentence we chose was our running example, very simple sentence, people laugh. Top down, bottom up, both processing were described. Now we describe the combination of top down and bottom up strategy because each has its own advantage and disadvantage. In top-down processing, we cannot have left recursion. Top-down processing also brings in useless grammatical categories onto the stack. Bottom-up strategies do not suffer from left recursion. They can handle left recursion, but they can bring in unnecessary or useless part of speech constructs onto the framework for processing. So when you combine them, we take advantage of the merits of both approaches. That means we reduce the application of useless rules and the pulling from the dictionary of useless parts of speech. Of course, one may say that if we do part of speech tagging correctly, then bottom-up parsing will be faultless. It will not have left recursion. It will not bring in the useless part of speech labels. And that is really true. In fact, the most powerful and elegant parsing algorithm is indeed bottom-up, the CYK parsing. So let's see the application of TDBU, that is top-down bottom-up parsing, also called chart parsing. What happens is that it is based on the notion of transitive closure. So we have this dot symbol here, which is called a handle in programming languages. In computational linguistics, we call it dot. So we know that as we uncover constituencies inside the sentence, the dot moves over that constituency. So we first are faced with dot and the two symbols NP-VP. That means dot sitting in front of NP says that I am now in the position of requiring a noun phrase to be uncovered. Now I know that to uncover a noun phrase, I'll have to either apply the rule NP goes to DTN or NP goes to N. The noun phrase can be found in two different ways. So I bring both the rules here, DTN and N. Remember that I only bring the rules. Okay, I do not apply them because that is controlled by the bottom-up parsing stage after this. So top-down and bottom-up, these two stages alternate in top-down bottom-up parsing. So we have to discover a DT or discover a noun. Now the bottom-up method kicks in. I see people. So people has to be resolved. Now in this case, we have NP goes to N, which is a production of the system, and the dot moves over N. In fact, this is correct because people is an N, is a noun. And I have found an N here, and therefore I have resolved NP goes to noun from the previous structure, which was these three rules, and I've applied NP goes to N. Now dot has moved over N. Since I have been able to resolve NP, now the dot from the first rule, S goes to dot NP VP. This dot goes over VP, no, over NP and sits in front of VP. This is shown here, S goes to NP dot VP. Now resolution of VP requires applying VP goes to V ADB rule. So dot sits in front of V and ADB, and VP goes to dot V. So VP can be resolved in two ways, verb, adverb, or verb. Notice that DTN was not applied because bottom-up parsing, the bottom-up stage of TDBU did not find a determiner. Fine. So now I apply V and I discover that laugh is V. So dot goes over V. So verb phrase has been found. And there has not been any more input. The dot has gone to the rightmost place in the first rule, S goes to VP, NP, VP. This means NP and VP both have been found, and therefore we have got success. Notice that VADV has not been applied. This would have been applied in top-down parsing if this rule came lexically before the other rule. So this very nicely illustrates how useless rule expansion is not done or useless part of speech is not brought. So we do know that people has both noun and verb part of speech, but you see in the chart here, no verb has been, verb part of speech has been brought. What is the reason? The reason is that we wanted to resolve NP. Okay, we did not have to resolve VP. There was no requirement of bringing in a verb onto the stack. Noun is fine. And also you can see in laugh, I did not bring in N into the chart at all because the task was to discover a V as is shown by the dot symbol sitting in front of the V symbol, which requires a verb. So this is also a very elegant parsing algorithm, which combines the merits of both top-down and bottom-up parsing. The arcs in parsing represent a chart which records the completed work, which is the structure to the left of dot, and the expected work, which is to the right of dot. Now, the same top-down, bottom-up parsing will parse quite well the whole sentence, people laugh loudly, where we have an adverb. So first S, NP, VP, and then NP goes to DTN, NP goes to N. All the three will come to the chart. Then NP will be resolved by people being noun. This will expose the requirement for finding a verb phrase. Laugh will supply that verb phrase. And then the dot will sit in front of ADB. It will not finish parsing because the input is not over totally. So ADB loudly meets that requirement. Loudly is an adverb. And so the dots goes to the end of S goes to NPVP, thereby parsing getting over. Now this bottom-up parsing idea is again the basis of another important parsing algorithm, CYK parsing algorithm, which was briefly alluded to in the last week. So we have here a segment of English, and this segment of English has these constructs. S goes to NPVP, NP goes to DTN, NP goes to NNS, NP goes to NPPP. That means the noun phrase can be formed in three ways: determiner and noun, plural noun, and noun phrase followed by preposition phrase. Preposition phrase is formed in only one way: preposition and noun phrase. Verb phrase is formed in two ways: verb phrase, preposition phrase, or PBD, which is a past tense verb, and NP. This grammar is an example given in Christopher Manning and Schultz's book on statistical NLP. The lexical rules are these: part of speech going to the actual words. DT goes to the, NN goes to gunman, NN goes to building, BBD goes to sprayed, and NNS goes to bullets. So we are required to parse using these grammatical rules. Grammar rules are context-free grammar rules. Is context-free grammar powerful enough to capture language? That is a question which has captured the thinking of linguists, computational linguists of the community. So context-free grammar, we know by application of pumping lemma, it cannot accept or generate strings of the form a to the power n, b to the power n, c to the power n. So this kind of sentences like Jack, Michael, and Mohan play tennis, soccer, and cricket respectively, where Jack is associated with tennis, Michael with soccer, and Mohan with cricket, cannot be processed in general. That is because A, B, and C, they themselves can be long sequence of words indicating complex phrases. So CYK parsing is a bottom-up parsing. We have to form a matrix-like structure where the rows start from 0 to the number of words. The gunman sprayed the building with bullets. There are 7 words, 0 to number of words minus 1. That is last but 1 index. And columns start from 1 and go to the last index. So thereby a cell inside the matrix indicates the position from I to j. Ith any cell ij indicates the language elements from position I to j. So when we start the parsing, we first resolve the, which is a determiner. Then we resolve we resolve gunman, which is between 1 and 2. You can see 1th row and 2th column. So NN there. Now DT and NN coming together one after the other can resolve a noun phrase. So this indeed is the case. We get a noun phrase between 0 and 2. The gunman is indeed a noun phrase. Similarly, sprayed is BBD, past tense verb. We get a DT between 3 and 4, the. We get building between 4 and 5, which is a noun. And a noun phrase gets completed between 3 and 5, the building. We get a preposition between 5 and 6 with, and a NNS, plural noun, therefore a noun phrase between 6 and 7. And then we form bigger phrases by combining smaller phrases. So P and NP combine to give PP from position number 5 to 7 with bullets. Then we get a noun phrase between 3 and 7, the building with bullets. Then we get a verb phrase between 2 and 7, sprayed the building with bullets. And finally, we get the sentence between 0 and 7. And that structure can be very easily recovered from the table itself. So the parse tree is obtained by keeping back pointers. So if we follow the back pointers, then we recover the parse tree in this way. The sentence is between 0 and 7. There is a noun phrase between 0 and 2, verb phrase between 2 and 7, PBT between 2 and 3, and so on. This structure gets created. The sentence happens to be structurally ambiguous. It can have another parse tree where with bullets is associated with either the building or with the sprayed. So who has the bullets, the gunman or the building? The syntactic tree tells me both are possible. Though semantics will tell me that building with bullets is strange. Sprayed with bullets is more natural. That is a frequentist approach, and that meaning is more frequent. So we'll stop here.